So hopefully you had a good weekend. I had a pretty uneventful weekend. I kind of overdid it a little bit yesterday with some work outside. Went up and cleaned out the rain gutters on part of my house. And that was a lot of up and down the ladder work, and so I'm kind of paying the price today. So anyway, we'll see how far we get today. Um, we've got one more topic to cover. Let's see where we are here. Come over here like this a bit. So we're going to open up chapter 4 today. We finished up chapter 3 on Wednesday, and I don't think there's anything more that we need to say about um, 3.3, which was the measures of um, position. And so I think we got that covered on Wednesday. So we'll open up chapter 4 this week, and that'll be a pretty smooth week. It's just one topic in chapter 4. It's kind of an involved topic. There's a lot of parts to it, but it's also a topic that it would be it, extremely helpful if you have just a basic background in algebra. And as I've probably said to you guys, I don't know what your math background is in this course. So we'll get into that into chapter 4. But a quick comment about the about the textbook. The textbook goes into it deeper into this topic deeper than I intend to, deeper than I do in this course. And they also do everything by hand. And we're going to be doing it on the calculator. The by hand calculations can be extremely lengthy and tedious, especially if you have a larger data set. Anytime you get more than 10 or 12 numbers in your data set, then the by hand method is just tedious. So, as I've said many times, that's the type of work that we're going to turn over to the calculator. And so I'll show you guys how to do stuff on the calculator today. And then another quick comment about calculator usage. We've been using the calculator since Wednesday of the first week, right? And several times I've talked about, hey, there's a module on our Canvas page titled Calculator Usage. There's some helpful videos in there. Go look at them. And over the weekend, somebody sent me an email and said, I'm looking for these videos. I can't find them. And I looked at our Canvas page, and silly me, I forgot to publish the module. So the videos were up and they were published, but the module itself wasn't published. And so I published the module, and I wondered, why didn't anybody say anything, right? If you guys couldn't find these videos last week before, it's like, wait a minute, nobody told me anything until this weekend. So anyway, it's there, and there are currently 3 things that are published in that module. The whole introduction to entering data in the calculator, one and using one variable stats is in there. The box and whisker plots that we talked about last time, there's a video in there for that. And then there's a video in there now for the topic that we're going to cover this week. So it'll be a pretty smooth week. We've got plenty of time to go through this work in chapter 4. A week from today, we have a holiday. And then Wednesday the 17th, we'll wrap up chapter 4. We'll talk about the exam, and exam 1 will post on that Wednesday morning after class. And then you'll have until midnight the following day to get the exam to me. So it's going to publish on Wednesday after class, and then it will be due by midnight on Thursday. So we'll give you plenty of time to do the exam. And again, I don't want to talk about the exam just yet. We'll talk about that on Wednesday next week. Okay, so that's what our next 3 sessions are going to look like. And yeah, I'll mention this. You guys have a holiday on Monday. I have a section of Math 12 that is Tuesday, Thursdays, starting at 8 a.m. And since you guys have a holiday on Monday the 15th, they're going to get what I call a pseudo holiday on Tuesday the 16th. Now, what a pseudo holiday means, and I don't think you guys have any pseudo holidays in your Monday Wednesday schedule, and I don't see any. But a pseudo holiday is where I host a session, but I don't present any new material. I'm just available to answer any questions. So that Tuesday morning from 8 to whenever, starting at 8 a.m., on Tuesday morning, I'll be running an informal Zoom session. And so you're welcome to check in with that if you have any questions that have come up about Chapter 4 or the exam or anything like that. And the sessions for my Tuesday, Thursday class, it's the same Zoom ID. I mean, it's the same link. The link that got you here, you can use that to join that Tuesday morning session if you would so like. Okay, so let's go over the quiz from last week because there were some common errors on that quiz, and I want to go over them. They're very important errors, and I've said a couple of times already, you guys are going to make mistakes, and I want you to make the mistakes on the quizzes. And in all three of my sections of Math 12, the majority of the classes, more than 50% of the students, made these mistakes on this quiz. And so I want to go over them very, very carefully, pay close attention. Before I do that, were there any questions coming up about our schedule? Okay. All right, so let's go over this quiz. So here's our quiz. And problem number 1 says, suppose the following data give the number of printers sold at all 10 locations of a certain store on a given day. And we're asked, okay, so there are the numbers. So 3 printers sold here, 7 sold here, 5 printers sold here, and so on. So the units in this data set are printers. Now, here's the first thing. It says find each of the following. Be sure to use the proper notation and units. That is critical. And we'll talk about what I mean by proper notation, what I mean by units. And then it does say round decimals to 2 places as necessary. So several people have asked about, hey, Jay, where should we round things off? And my answer is, if it's important to me where you round off, it will say so in the instructions. If it doesn't say where to round off in the instructions, round to 1 or 2 places, whatever feels right to you. So we're asked to find these things here. So we want the mean. Okay, now I just took these 10 numbers and I sent them through one variable stats, and I got a mean of 5.1. It says the one variable stat says X bar is 5.1. Okay, but we need to know that we're treating this as a population. And there's that key word right there. It says all 10 locations. And what you'll learn is, how do you tell whether it's a sample or a population? And I'm telling you that, watch for some key words. And this is a key word right here, all. And so this is to be treated as a population. So the correct notation, or the proper notation for the mean, is mu. That needs to be there. So when it says be sure to use proper notation, we need that there. If we are treating these 10 numbers as a sample, this would switch to X bar. And then 5.1 what? Printers. That's the proper units. Be sure to use proper notation and units. So the units here are printers. Now, sometimes people look at that and say, well, what the hell is 5.1 printers? You can't, sell 5.1 printers. It's important that you keep in mind that even if the data are discrete, whole numbers only, it's possible for the summary statistics to have decimal values. So don't freak out if you get a decimal value for data that are discrete. So mu equals 5.1 printers, median is 4.5 printers, the mode is 4 printers. Standard deviation, again, we need to pay attention to, is the data set a population or a sample? And we're treating it as a population. And so the correct standard deviation is sigma, that's the proper notation. 1.87, I rounded that to two places, and the units here are printers. For the variance, I was saying, well, once you have the standard deviation, just square that and you'll get the variance. So the proper notation for the variance is sigma squared. Comes out to be 3.50 printers. I rounded that to two places. And it's the units are printers squared, or square printers. And as I said, probably 2/3 of the students missed a point or two for not using proper notation and units in these answers. So make sure that you understand what that means, because that type of mistake on a quiz costs you 1 or 2 points. Same mistake on an exam is going to cost you more. So don't make the same mistake on the exam. All right, now the next question is this data set symmetric, skewed left, or skewed right? We now have three different ways of identifying skewness in a data set. And I went with the one that was most direct. I looked at the relationship between the mean and the median. I don't have a histogram here. I haven't drawn a box and whisker plot. Um, I'm just looking at the relationship between the mean and the median. And the mean is greater than the median, and so that's an indication of it being skewed right. And again, you got to back up your answer somehow. This is actually enough justification or explanation, if you will, for why I'm saying skewed right. Okay, so that's the first problem on the quiz. Any questions about that?
I have a question about the point system.
Yeah.
If we give proper notation, but our numbers are wrong, I noticed on my calculator, I just went back and checked my like numbers, and I had like I hadn't cleared the list all the way, so I'd gotten some skewed numbers, but my units were all correct. Will we miss both points due to like incorrect numbers, or is it just one?
I'd have to look at your specific quiz, and I'm happy to do that either after class today or during office hours. We can do that. Um, it takes me a couple 10-15 seconds to pull up your quiz and see what your submission looked like. But that's the best way to um, to answer specific grading questions. In terms of, I need to be honest with you guys, grading is not a perfect science. And, where somebody lost 2 points and somebody else lost 1 point, yeah, that kind of shit happens. So I'll apologize ahead of time for that. But when we're talking about, a discrepancy of 1 or 2 points, it's not going to make any difference in terms of your final grade. So don't worry so much about 1 point or 2 points taken off. Focus more on what it is that I'm complaining about. And I promise you guys, at the end of this semester, when it's time to assign grades for the course, if anybody is 5 or 10 points short of a grade, I will throw in 5 or 10 points without hesitation. Nobody's going to miss a C grade in this class by 5 points. Come on, man. I'm going to throw those points in there just to make up for any weirdness that may have happened with grading along the way. Um, and it's also difficult to I don't spend a whole lot of time deciding, is it -1 or -2 for this? But let's, like I said, let's go back and look at your specific quiz. And if you think that I've ripped you off of points, let me know, and we'll discuss it. I'm a reasonable guy, and and I'll make good if I have been a little heavy-handed with the red pen, so to speak. Okay, so
Thank
let's
you.
go. Yep, yep. So
Hey,
let's
I
go.
had a quick
Oh,
question.
go ahead.
Um, so we don't, since we're using our calculators, we don't need to show our work, right? We just need to have the proper notation instead.
Yes.
And do we need to put like maybe at the top of the problem that like, oh, like we used our calculator and used this setting on our calculator? Or does that,
That would be awesome.
okay, great.
That's a beautiful thing to do, right? And a lot of times I will, write down the phrase via one variable stats, or something like that. So, yeah, I'm kind of operating under the assumption that you are using your calculator because,
Right.
that's the way to do it, man. I mean, that's the way to do it. So,
Okay, thank you.
yeah, yeah. Um, okay, so let's go on to this next problem. It says, suppose the ages of employees at a certain college have a bell-shaped distribution. That's key, bell-shaped distribution with a mean of 45 and a standard deviation of 9. What percentage of the employees at this college, and we've got these questions here, are younger than 54, are between 27 and 54. And it's key that we have a bell-shaped distribution here because that means we can use the empirical rule. And we can draw that nice bell-shaped distribution. We can indicate 1, 2, 3 standard deviations either way. And so that's my hint here, pardon me, that pictures might be helpful. So I went ahead and drew these pictures. Let's see what I've got. Let me slide this up. So I went ahead and drew these pictures here. Here's our bell-shaped distribution. It's a nice touch to put that X on there. I'm going to encourage you guys to do that, get into a good habit right from the start. So here's our mean at 45. Standard deviation is 9 years, so there's plus 9, plus 9, plus 9 gets us up to 72. And what we're saying in this picture is there's virtually nobody at this college who's older than 72. No employees at this college older than 72. And then here's minus 9, minus 9, minus 9. Same thing is true for 18 years old. Are there employees at this college that are younger than 18? Extremely unlikely. So we're saying that 99.7% of the employees at this college are somewhere between 18 years old and 72 years old. All right, now, younger than 54. So there's 54 right there. And so I've shaded all of the area to the left of that 54. And I need to figure out, okay, well, what chunk is that? What piece is that? And I know that to the left of 45, this left half over here, that's 50%. And then we argued from the empirical rule that plus minus 1 standard deviation will get you 68%, about 68% of the employees. And so by symmetry, between 45 and 54 is half of that 68, which is 34%. So you add those up and you get about 84%. Okay? And then same type of picture here. We're going in between 27 and 54. So we know that this piece right here, again, is 34%, about 34%. And then I'm making the same type of argument that I made. And I'm saying, well, between 27 and 45, that's half of the 95% coming from plus minus 2. So that gives you 47.5%, plus that 34% there gets you about 81.5%. Okay, now that we can do it that way because we are told explicitly that we have a bell-shaped distribution. Okay, so now here's where, so this one went pretty smoothly. Number 2 looked pretty good for most people. But then we get into number 3, and there were 2 important mistakes made here, and so I want to be clear what those are. It says, suppose the ages of students at a certain college have a distribution with this mean and that standard deviation. And it says, what percentage of the students have ages between, 16.7 and 36.9? And there's nothing in this problem that tells us anything about the shape of the distribution. We're just told, hey, we got a distribution here with this mean and this standard deviation. So we cannot assume that it's a bell-shaped distribution, which means the empirical rule cannot be used here. We cannot assume a bell-shaped distribution. If we don't know anything about the shape of the distribution, the best we can do is use Chebyshev's theorem. And so I organized this as follows. We did one of these in class. And I said, okay, here's our lower of 16.7, here's our upper of 36.9, and our mean of 26.8 is somewhere here in between those. And then a little bit of arithmetic says, hey, this range of ages that we're asking about is plus minus 10.1 years. And we have to figure out, okay, well, how many standard deviations is that to use Chebyshev's? And so I took that 10.1 year difference and I divided it by 4.6 years. That's the standard deviation. And I got 2 point, some numbers here. And I said, let's call that 2.2. So I just rounded that off to 2.2. That's good enough for here. And so that's the value of K. So then we go talk to Chebyshev. And Chebyshev says, hey, you need to run this calculation. So I did, and there's the value that I got. And this one I decided to round it off to 3 places. So I wrote it as 0.793. And that translates into 79.3%. And way too many people missed these key words right here, at least, and just told me, oh, 79.3%. But I pushed really hard on this when we were covering this probably a week ago. I think we covered the empirical rule in Chebyshev's on Monday last week. So, and I invite you to go back and take a look at that lecture from a week ago, and you will see that I emphasized heavy that those words at least need to be there. So the question is, and I'm not disparaging any. Where are the reaction icons? I don't see them. Anyway, I hope you guys can still hear me and see me.
I can now. It just cut out for a little bit, but you're okay now.
Zoom is winking out on me. Okay, I guess we're back. Can you guys? You guys can hear me? Are you guys there?
Yeah, we can hear you now.
All right. So I don't know what the hell happened there, but I got a little thing on my screen that says your internet connection is unstable. And then Zoom booted me out, and I tried to come back in, and it booted me out again. And here we are back. Okay, so let me try to keep going here. So I may have mentioned this on the very first day. If we run into technical difficulties of that nature, just hang on. Give me 5-10 minutes to come back to life or something like that. It doesn't happen very often. I think it happened once all last semester. So, we'll hope for the best. But if my internet takes a dump, then I have to restart my router or my modem or whatever the hell that box is called, and then it it takes a good 5 minutes or so, 10 minutes or so to come back to life. All right, so let me see if I can do a screen share again to bring that camera back. Okay, so that seems to be back. And then we'll come back, bring this up. And it says that the meeting is being recorded, so that's good. And let's bring this back. Okay, so we've got that. We've got that. Okay, so fingers crossed, hope for the best here. I guess, were there any other questions about the quiz? Okay. So what I will then do is move us to the boards and open up the stuff for chapter 4. Let's see, are we ready? Yeah. Okay. So, whoops, sorry. So let's cover up that. And that's me turning my desktop computer. Let me turn that light off. And, when I leave my desk and move to the boards, I turn my desktop computer 90 degrees so I can see it when I'm standing up here at the boards. And last semester, when I was first learning how to do this, let me change one more thing here. Let's see, what is that? That's what I want, but it doesn't seem to be having any effect. So one of the first times that I turned my computer so that I could see it when I'm up here at the boards, instead of sitting down at my desk, I managed to pull the power cord out of the back of the computer, and everything was dead. And that took me a good, just about 10 minutes to come back to life from that one. So I learned my lesson, I made the mistake, I won't make the same mistake again, and so now it will not happen that I unplug my computer when I turn it like that. Okay, so here's what's up on the board. Let me stand out of the way here, take off this shirt. And so what chapter 4 is about is what's called regression analysis. And here we want to predict the value of one variable that we call the response variable based on values of other variables. And the other variables, we call those the explanatory variables. And what you'll see is that there will always be one response variable, but you can have multiple explanatory variables. And so here's my first example. I thought of this example because I think end of last week, I was talking to a student, and the question about, okay, how much time should we be spending on this course and things like that. And we kind of came up with about anywhere from 6 to 10 hours a week, studying, doing homework, going over notes, rewatching lectures, things like that. And so I thought, okay, well, let's extend that. So let's suppose that you want to predict how many hours each week a student will spend studying. What would you want to know about that student? So imagine yourself as a counselor or an academic advisor or something like that, and a student comes to you and says, well, I'm going to take classes at Cabrillo. How many hours a week should I anticipate that I'll need to spend studying? And So what we've got here, let's do the vocabulary here. Let's come over here and we'll say in this case, the response variable is going to be hours spent studying. So that's what we're trying to predict. And my question is, what would you want to know about that student? Now we're talking about the explanatory variables. Sorry. See if I can spell that correctly. Explanatory variables of ours. Come on now. So I'm a little bit shaken and out of sorts right now because of all of that technical difficulty. I don't like it when that happens. So the explanatory variables. And you know, this doesn't work very well in this online setting, but you know, if I were in a classroom, I'd just put the question out to everybody in the room and say, okay, well, you know, what contributes to the number of hours somebody's going to spend studying? What would you want to know? And I think I'll just do a little bulleted list here. Let's see, how many units? You know, how many units is this student taking? Are they taking just one 5-unit class? Are they taking 12 units? Are they taking 18 units? I think that would have something to say about how much time you spent studying. You know, and you're welcome to turn on your microphone and you know, shout out an idea of, oh, I'd want to know this, I'd want to know this. Like I said, I've done this lecture once in an online setting, and it didn't work very well for that, but you're welcome to do that, of course. I might want to know what that person's major is. So number of units, what's their major? You know, are we talking about somebody who's taking 12 units of physics classes, 12 units of English classes, 12 units of PE classes or kinesiology, whatever the hell they call it these days? So I might want to know what their major is. I might want to know, oh, I don't know, I'm just kind of brainstorming here. These are some of the things that students have said in the past. You know, when I was doing this lecture in a classroom, you know, somebody's, you know, said, I want to know what their GPA is. Are we working with a student who has a 3.5 GPA, a 3.9 GPA, a 2.1 GPA? Because that might be an indication of how serious they are, or, you know, things like, you know, are they a student who really puts in, you know, lots of time?
Are extracurricular activities included, like athletics or jobs, or is it just like how they are as a student?
Yeah, that's a good one. So how about other commitments? You know, are they working? Do they have children or parents that they're taking care of? You know, I mean, something like that. So are there other commitments, outside commitments? I don't know. Anything else jump out at you that you might want to ask this student? Nah. So there's 4, you know. And so what we've got, what I was just saying is, you know, we've got one response variable, but you can have multiple explanatory variables, right? So another way of looking at this is, if you see a situation, you say, why is this happening? Why is this thing increasing, or is this thing decreasing? You know, and I don't want to talk about this too much, but if you know, what we've seen over the last several months is a tremendous increase in the number of COVID cases. and things like that, number of hospitalizations, and you go, oh shit, this is increasing, this is going up. What's causing this? What explains this increase that we're seeing in the number of cases? Typically, it's not just one thing, right? It's, you know, you can't just say, oh, the increase in number of cases is due to this and this only. No, man, there's usually a number of things that are in there. So it's quite common to have multiple explanatory variables for one response variable. Okay, here, let's just put out another example here. Cost of car insurance. You know, if somebody's saying, well, I'm thinking about buying a car. I've never had a car before. I'm going to buy a car and I'm concerned about how much my insurance is going to cost. You know, so our response variable, I'll just abbreviate it RV, is going to be the cost. And in terms of the explanatory variables, what are the things that influence or impact cost of car insurance? I don't know, how about somebody's driving record? Well, if it's a person who's buying their first car, they've never had a car before, they may not have a driving record. Okay, well, how about age? Because I can tell you for a fact that you younger people pay more for car insurance than an old dude like me. You know, I've got a very good driving record. I'm old, and so my insurance rates are probably significantly lower than yours. And I know this to be a fact because when it came time to get my daughter on my car insurance policy, you know, that was a little sketchy. How about age or gender? Whether you like it or not, whether somebody identifies as male or female has an influence on how much they spend, how much they pay for insurance. And you know, related to this is like motorcycle insurance. If an 18-year-old male gets motorcycle insurance and an 18-year-old female gets the same motorcycle insurance, the guy is going to pay more than the female does. And that's just the way the insurance companies work. What else could it be could explain cost? How about your location? Where do you live? Where will the car be kept? You know, are we in a sketchy part of town? Are we in a good part of town? Are we in a, you know, a sketchy part of the state or a good part of the state, something like that? And so your location, typically they want the zip code for, okay, where's the car going to be? For motorcycle insurance, I can tell you that they want to know whether the motorcycle is kept outdoors or whether it's garaged. That makes a difference in terms of cost of car insurance. Okay, so there's 4 possible explanatory variables that I've just kind of brainstormed. All right, now let's get back to the mathematics behind this. I'm going to come over here and I'm going to put a note up here. And so I'll just put note. Multiple explanatory variables make the mathematics complicated. And I won't go into the mathematical theory behind this, but if you have one variable, mathematically that's what we call a one-dimensional problem. If you have two variables, like one response variable and one explanatory variable, you have two variables, we have a two-dimensional problem. And that's a common thing that we do in algebra and pre-calculus and calculus, is that we look at two variable relationships. You guys might have heard of the XY plane and graphing lines and things like that. Every time you add a variable, the number of dimensions goes up. So if you have two variables, it's a two-dimensional problem. You got three variables, it's now a three-dimensional problem. So for example, in this first situation right here, we have 5 variables. We've got one response variable, 4 explanatory variables. That's a 5-dimensional mathematical problem. That shit can get real complicated. So what we're going to do in this class, mathematically, we're not ready to tackle a 5-dimensional problem. We will use only one explanatory variable. Variable. That is, in this class, we will do simple regression analysis. It's what it's called. And simple regression analysis is where you have only one explanatory variable. If you have multiple explanatory variables, that's what's called multiple regression analysis or multivariable regression analysis. Kind of complicated. We'll do simple regression analysis. Moreover, we're going to simplify it even further, and we're going to do what's called simple linear regression analysis. Let me add that in here. Sorry, I should have anticipated this. We will do simple linear regression analysis. And what our goal is going to be is to find the equation of a line, technically what's called a linear function. Find the equation of a line that best fits the trend shown in our data. So our goal will be to find the equation of the line that best fits, we say, the trend shown in the data. Best fits. All right, now what the hell do I mean by that? So we will have what's called bivariate data, which is a fancy way of saying data that consists of two numbers, pairs of numbers. Our data will look like what we call ordered pairs. And I started today by saying, you know, this topic, while not super complicated, is easier if you have some basic background in algebra and the idea of ordered pair notation, equation of a line, things like that. These are things that we typically cover in, let's say, an elementary algebra class or a first algebra class. So every one of our data values will consist of a pair of numbers, and this second number is going to be the response variable, and the first number is going to be a value for the explanatory variable. Okay, now, and let's go back to this guy right here. Let's go back to this first example. You're trying to predict how many hours per week a student is going to spend studying. And we have identified 4 possible explanatory variables. And I'm saying you can't have 4. You can only have 1. So of those 4, you have to pick 1. And then this is kind of the tricky part, because you say, okay, well, which one would I choose? I can only have 1, and I want to choose wisely. And so what you do is that you look at these things and you say, okay, well, which one of these things do you think would have the greatest impact of the 4? Where would you get your biggest bang for the buck, so to speak? And I'm going to argue for this one right here. Now, again, don't get me wrong. I'm not saying that these other 3 don't play a role in terms of how many hours a student's going to spend studying. But I'm going to say that I think units is the number one thing that I'd like to know. If I could only know one thing, I want to know how many units you're taking. Because that way I can come up with a simple prediction for how many hours that you'll spend studying. Is it going to be a perfect prediction? No, but it'll be legit. So, for example, if we go hours, that's something different. Hours spent studying versus number of units. We might have an ordered pair that looks like 12, 15. And that's the way we're going to organize the information. And we're going to say, okay, if a student has 12 units, we're going to predict that they will spend 15 hours per week. So this would be 12 units. And this would be 15 hours per week spent studying. And so how do we come up with the data is that we could simply go and ask, we could sample a bunch of students and say, how many units do you have? How many hours per week do you spend studying? And if we ask a whole bunch of students, we get a whole bunch of these ordered pairs. And then what we're going to do is we're going to plot those ordered pairs in the XY plane. Let me come over here and draw you a picture. So to quote unquote see the trend in the data, we'll typically create what's called a scatter plot. A scatter plot by plotting has one T or two T's, by plotting the ordered pairs in the XY plane, it's called. So what we're going to have is we're going to have an x-axis and we're going to have a y-axis. And each one of these ordered pairs that we have that makes up our data set will give us a point. It'll be a value of x and a value of y. So I'm just going to make up some points here. So we got, let's say, a point there, and we got a point there, and we got a point up here, and we've got a point there, and we've got a point there. I suppose we got a point right there. So what we see here is a general upward trend. As the value of x increases, moves to the right, the values of y get higher. And so we see a general upward trend. And so our goal in doing simple linear regression analysis is to take that trend that we see and come up with some line in here that comes closest to all of these points. I'm just going to eyeball it and say, maybe about right there. Come on, stick. A little shaky, but. And so that green line that I've drawn right there is what we call the line of best fit. It looks like it's a little bit low to me. I kind of stumbled in drawing that. Maybe it should be a little bit higher. But fortunately, we won't be finding this line by hand. We'll get the calculator to do it for us. Okay, so that's going to be our goal, is to find the equation of that line. Now let me just glance at my notes here. I'm a little bit scattered here. I want to make sure that I'm not missing anything. Okay, so we've got that, we've got that, we've got that. All right, so that'll be all right. And we've got that. Okay. So what I'm going to do is, let's see. I don't know, it's a little bit scattered what I've just done here. So hopefully this is making some sort of sense. Do you guys have any questions at this point in time? Because I'm going to go ahead and take a short break. I'm going to move the camera back to the document camera view because I want to show you guys, I want to do this first example the first example of this type of analysis. I'll start by doing it with the document camera. But do you guys have any questions? Actually, let me come and sit down and answer any questions that you guys might have before I send us on break. Okay, so do you guys have any questions at this point?
If we use more than one variable or explanatory variable, would we have to have multiple graphs? Or
Yeah,
how
man, it gets the mathematics, the gets really complicated And the visualization is really complicated as well. So like I said, it's something that we're not ready for. And to do what's called multivariable regression analysis technically requires some advanced calculus techniques and also some knowledge from linear algebra, which is in the math department at Cabrillo, that's Math 6, which is a course that is typically taken after you finish the calculus sequence. So it's just way too complicated right now to turn this course to multiple variable analysis. If you're interested in seeing multiple variable analysis, it is covered briefly in our textbook. I don't believe that the first edition of the textbook does multiple variable analysis, but I believe that the second edition does, and the third edition definitely does. I don't know about the second edition, but the third edition, they definitely do talk about multivariable regression analysis. So if you're interested in it, you can go look it up in the book. I honestly don't know very much about it. I was just introduced to the topic about 3 years ago, and I haven't had a whole lot of time to dig into the topic and totally understand it myself. So even if if you say, oh, I like this, and you go and read about it in the book, and then you come back to me and say, oh, can you explain this? The answer is going to be no, sorry, I can't, because I really don't know how to do multiple variable analysis. It's doable. I mean, you can learn how to do it, but I have not yet done that. I've been busy doing other things, and
Understandable.
yeah,
Okay, thanks.
sure. Okay, so what I'm going to go ahead and do then is send us on break for 20 minutes. And then when we come back, we'll start looking at our first example of simple linear regression analysis. Okay, so let me go ahead and pause the recording. No, come back here. Try that again. Pause the. Be interesting to see what this recording looks like. Due to considering our technical difficulties, um, I'll take a look at the recording and see if I have to apologize for any language that I may have used, because my speech gets a little colorful when technical difficulties enter our realm. Okay, so here's the situation that I want to start looking at is, and this may be an example in your textbook, I'm not sure, but the number of manatees killed is increasing, and the question is, why is this happening? What's causing this? And so hopefully you guys know what a manatee is. A manatee is a slow, large water creature that swims in the shallow waters, primarily off the coast of Florida. And they've got a lot of things working against them. They are large, they are slow, and they swim in shallow waters. So at some point, people really started paying attention to this and saying, hey, we got a problem here. We got a whole bunch of dead manatees, and what's going on here. So what I want to do is go and look at this from a simple linear regression analysis point of view. And what I'm going to do is identify our response variable. This is the one that we are trying to predict. The response variable will be the number of manatees reported killed in Florida. And we need to kind of brainstorm possible explanations for this, possible explanatory variables. And, one argument that has been made is it comes down to overcrowding, more people. So many problems that we face in the environment. People keep coming back to population growth as being, the number one culprit there, human population growth. Some people will argue, well, the waters are becoming more polluted. We've got runoff from rains and things like that. And in some areas, the Gulf of Mexico in particular, there are large what bacteria blooms or algae blooms from fertilizer being washed down the rivers and going into the Gulf. Some people are going to argue, well, the number one threat to manatees are power boats, and and that's a strong argument, because that is one of the main issues, is because these creatures swim in shallow waters where recreational boating is quite popular. That's a problem. Some people argue, well, it's an issue of awareness. 100 years ago, nobody gave a shit about the manatees. They weren't paying attention or anything like that. But then, the 1970s came in and everybody got environmentally conscious and stuff like that. So maybe people are paying attention more. And somebody argued for, well, dude, there's just more manatees, and it's a circle of life. The more manatees there are, the more manatees will die. And so, we're back to the problem that we were talking about before the break, is if you try to bring in multiple explanatory variables, well, then the mathematics and the analysis gets quite complicated. And so it's sort of like, well, if you want to do this at the most basic level, which is where we are, well, nothing wrong with that, that's where you start, is that you've got to pick just one of those. And now, this is open to debate. If you had to pick just one of those five, which one would you choose? And I was saying before the break, we want to choose wisely. Now, we may make our choice, and we may find out that, hey, we have chosen poorly. We chose an explanatory variable that didn't, after we go through our analysis, it's not really telling us much. Okay, well, then you go back to the drawing boards, and maybe you pick a different explanatory variable and you run the analysis again. But you got to start somewhere with just choosing one of them. And so for this discussion, I'm going to choose that middle one, more power boats. So what I want to do is look at the number of manatees reported killed in Florida versus the number of power boats that we've got. So that's the analysis that we're going to run for this example. Our explanatory variable is going to be the number of registered power boats in thousands in Florida. And we don't do a whole lot of error analysis, what's called error analysis. But I'm going to argue that one of the reasons to choose power boats as your explanatory variable is because we can easily gather data on that. Now, that said, there's no way that we can gather data for how many boats there are in the water at any one time. The best we could do is go to the Department of Motor Vehicles or whatever the hell it is in Florida and look up data on the number of registered power boats. And that's going to allow for some uncertainty to enter into our analysis. Because is it possible that a power boat is registered but never sees the water? Yep, could be sitting in the driveway for years and years and years, never makes it to the water. Is it possible that there's a power boat in the water that is unregistered? Yes. So, when you go in and you do a full professional analysis of this type of data, then you bring in those issues as well. So what I've got here is the following data set. Now, this document that I'm using here is available on your Canvas page. And so what we have is we have some bivariate data, two variable data from 1990 up to 2007. So this is just a snapshot of time, but it's a data set that's not super large, and we can go ahead and work with it. Now, what the values of X represent, we've got to be crystal clear about the definition of our variables. So it's the number of registered powerboats in thousands. So in 1990, there were 719,000 registered powerboats in the state of Florida. So that's not 719 boats, that's 719,000 registered powerboats. That's what it means for the variable to be in thousands. And there were 47 manatees reported killed. Now, in terms of also error creeping into our data set, is it possible that a manatee is killed and goes unreported? Sure, so there were 47 reported there. 1991, number of powerboats, 681,053 manatees reported killed, and so on. So if you want to follow me on your own calculator, you're welcome to put this data into a couple of lists. I have done that on this calculator, and I've gone into Stat, Edit, and I have put in list 1, I have put the powerboat numbers, and I just put them in as they appear on this document. And then in list 2, I have put the number of manatees killed. We'll put that data in there. So as I said, this document that's under the camera here is currently available on your Canvas page. So you're welcome to print that out if you want to have that. I will leave this data set up on this document camera for a little while if you want to go ahead and enter that into your own calculator. If you're saying, oh, Jay, that's a pain in the ass, I don't want to do that right now. Okay, well, do it later at some point if you want to reproduce the analysis that I'm going to show you guys. Okay, so if you want, I'll wait a minute or so if you want to enter those numbers into your calculator. And I'm just going to very quickly double check, make sure the numbers are all legit. Okay, so and here's a little tip, a little bit of advice. If you're entering data into your calculator, it's not a bad idea to go back and just double check the numbers and make sure that they've all been entered correctly. I mean, it sucks to go through an entire analysis and then realize that you typed in a number incorrectly. So it's just a good idea to double check your data and make sure that you got everything in there. Another thing that's a nice idea to check is to make sure that your lists are the same length. Because what I'm about to ask the calculator to do is to turn these two lists into a bunch of ordered pairs. And so it has to be able to grab a number from list 1 and pair it up with the number in list 2. So if your lists are different lengths, the calculator is obviously going to complain. So double check and make sure that the numbers have all gone in correctly. And I want to show you guys how to do basically 3 things. And I want to create a scatter plot for this bivariate data. Then I'm going to ask the calculator to find the equation of the line that best fits the scatter plot. And then I'm going to go ahead and graph that line as well. So I'm going to show you guys how to do three things. And as I go through this, if I lose you, don't freak out. You can come back and rewatch this part of the lecture if you need to. Also, on our Canvas page, we've got that calculator usage module, and they show how to do at least the finding the equation for the line. They show that in that linear regression example. I'll see if I can find another YouTube video for how to create a scatter plot and stuff like that. But what I'm going to do to create this scatter plot is that I'm going to go to stat plot. So stat plot is where we were going on Wednesday, and that's where we created a box and whisker plot that I drew for you guys on Wednesday. So and I need to pay attention to where my numbers are. So list 1 and list 2, okay? Remember that. So if I press second and then the y equals button, that will get me up here into stat plot. And when you go to this screen, there's a little summary of what's going on. So there's plot 1, plot 2, plot 3. There are 3 plots built into the calculator. And right now, plot 1 is turned on. It is set up to do a box and whisker plot using numbers in list 1. A box and whisker plot that will show outliers using the numbers in list 1. I want plot 2 and plot 3 to be turned off. I only want to have one plot turned on at a time. So let's go in and work in plot 1. So if I press enter, then I'll go into the details of plot 1. And as I said, right now, the type of plot that's selected is a box and whisker plot showing outliers. I want this first type right here. So make sure that this plot is turned on. It is. And then come to this first type, put the cursor on there, press enter, and it will select that type. And then what you have is X list and Y list. And the X list has to contain your explanatory variable, and Y list has to contain your response variable. So X list is good. It's set at list 1. I don't know what the hell Y list is, but I want that set at L2. So let me go ahead and bring this calculator up a little bit higher. So to get, sorry. So to get L2, it's up above, right, the 2 button. So you press second and then the 2 button. And now I've got it at list 1 for the X list, list 2 for the Y list. And then you come down here and you have a choice of 3 different types of marks that the calculator will use to create this scatter plot. You can use a box, you can use a plus sign, or you can use a dumbass single dot, 1 pixel that nobody will ever be able to see. So I like to use that plus sign right there. Okay, so the plot is now set up. The next thing I need to do is to set up my window boundaries, because left and right is going to be the x-axis, up and down is going to be the y-axis. And watch carefully, there's a really slick way to do this. And it's up here in this very top row of buttons, there's a button labeled zoom. And so if you press the zoom button, and then you come down to option number 9, I believe. Yes. Option number 9 is something called zoom stat. And what it will do is it will look at the type of plot that you're trying to draw. It'll look at the numbers you're planning on using for that, and it will automatically set up the window boundaries for you. So if you select that, press enter with it on zoom stat, then you should get, if everything's lined up properly, you should get that scatter plot right there. Now, you might get an error message there. If you get an error message, then obviously something is not right. Either the plot is not properly set up, or there's a problem with your data. And typically the problem with the data would be that the lists are different lengths. But if the lists are good and the plot is set up correctly, then you should get a nice scatter plot like that. Now, unfortunately, what this is showing is a general upward trend. As the number of, so X left right is the number of registered power boats, up down the Y is the number of manatees killed. So as the number of power boats goes up, so does the number of manatees killed. So we see this general upward trend here. So as I said, our goal is going to be to find the equation of the line that best fits that data set. And let me show you how to do that. And that video, that YouTube video that's on our Canvas page, will show you how to do this very nicely. So what we're going to do is that we're going to go and press the Stat button. And we're going to go over to the Calc menu. And we've been here many times before. Our old friend One Variable Stats is there. But I'm going to scroll down in this list and I'm going to find the linear regression command that we want to use. Now pay close attention to this. Option number 4 says linear regression, linreg, that's linear regression, and then it tells you the form that will be used for the equation of the line. And so this form is ax plus b. This is not the one we're going to use. So under no circumstances should you use option number 4 to do this analysis. Keep going. We're going to use option number 8 in this class. And that's a linear regression command, but the form is different. It's a plus bx. And that's the form that we want to use in this class. Again, I want to say this very clearly. Do not use that form right there. Always use option 8. Okay, so if I press enter on that, then it will bring me to this screen. Now this is what the newer calculators look like. If you're using an older calculator, it has a slightly different interface, and you can see instructions for that on that YouTube video on our Canvas page. XList is list 1, YList is list 2, and it's critical that you use the correct lists here. Now, frequency list and store regression equation, you can leave those blank, okay? And so if everything's set up here, then we can press enter on calculate, and if everything's cool, it'll go through and analyze that bivariate data and give you this equation here. Let me grab a piece of scratch paper to use here. Let me slide this over a little bit, and let me write here. So the equation, the form that we're using here is y is equal to a plus bx. And again, here's a place where it's nice to have a little background in algebra. So the value of b is what's called the slope number. It's the number that measures the steepness of the line. And this value a right here is going to be what's called the y-intercept. And what the calculator is telling you, it says, hey, your y-intercept, the value of a, is negative 31.99, blah, 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 lots more digits. I'm just going to call that negative 32. That feels like a good place to round off. And it's going to say, and your value of b, your slope number, is 0.1153 and some change. It's a little awkward to round off here, but I'm going to go ahead and round off to 0.12. And as I said at the start today when we were going over the quiz, if it's important to me where you round off, it'll say so in the instructions. But typically, if I need to round off here, I'll round off to 2 places, sometimes 3, rarely more than that. So what that means is the equation of the line that we seek is y is equal to negative 32 for A plus 0.12 times x. And again, x is our explanatory variable and y is our response variable. And I want to be crystal clear about this. X is our variable that refers to boats, and y is our variable that refers to manatees. So a value of x will refer to the number of registered powerboats in Florida in thousands, and the value of y will represent the number of manatees killed based on that number of boats. All right. So what I've shown you is how to do 2 of the 3 things that we want to be able to do. The first thing was to create a scatter plot. The second thing here is to come up with the equation of this line of best fit, we call it. And then the third thing that I want to show you guys how to do is, let me go back to the calculator here, press graph. There's our scatter plot that shows that general upward trend. What I also want to do is ask the calculator to graph this line. And where you go to do that is to just this y equals button right here. You don't press second y equals. Second y equals gets you into stat plot. You just press y equals. And it'll bring up a place on the calculator where you can graph functions or graph equations of functions. Now this is left over from a pre-calculus class. I'm going to clear that out. I'm going to press clear, and I'm going to enter this equation in its place. Now, watch very carefully. This starts with a negative 32. To get a negative 32, you do not press this subtraction button. This guy down here in the very bottom right corner is how you get a negative number on this calculator. So you press that guy, 32 plus 0.12, and then we need an X up there. And just to the left of the stat button is a button labeled XT, theta, and N. If your calculator's in the proper mode, which it probably is, and you press that guy, you'll get an X showing up, and that X needs to be there. Okay, so now that I have that equation of this line in there, I can come right back to the graph button and say, okay, graph this. And so there you go. There's that general upward trend shown in the scatter plot, and there is the mathematically best fit line that goes through that scatter plot. Now what happens is that line obviously misses many of the data points, but some of the misses are below, some of the misses are above. And so what that line effectively does is that it averages all those out and it minimizes the differences between the equation of the line and the actual data points. And it's an interesting problem from calculus to come up with this equation. For people without a background in calculus, well, it's been boiled down to formulas that you can use. And if you're interested in seeing the formulas for coming up with this value of A and that value of B, you can look up those formulas in the book. As I said earlier, they're tedious by hand calculations. And we've got a fairly large data set here. I think we have 18 years worth of data. And, oh man, it's just a pain in the ass to do this by hand for a large data set like that. Okay, now, the next step is to take this equation and do some mathematical analysis on it. And so if everybody's cool, I'm going to move back to the boards and start to show you what that analysis will look like. Okay? Any questions up to this point so far? Okay, so let me do just that. Let me move to the boards. And we'll take this, I'll take this calculator, bring it over here. Actually, bear with me just one quick second. I need to do one thing before I move the camera. Hang on just a second. Okay, so I can move this computer like so, and I can move the camera now. Go back to the boards. Okay, so we got that. Looks okay. Hang on, my kitty wants to go outside. Now that it's sunny and warm outside, she wants to be outside. I don't blame her. Okay, everything's cool there. That's good, that's good, that's good. All right. So let me erase this panel over here. And we'll see how far we get with this today. But we'll probably be able to do a good chunk of this analysis today, and then we'll need to finish it up probably on Wednesday. And then once we finish it up on Wednesday, we'll bring out another example and go through another problem. Okay, so when we, let's see, how do I want to say this? I guess I'll do it like this. I'll try this. So note, once we have the equation for what we call the line of best fit, let me underline that. And there are other names that we use, and I'll put those up on the board at some point. But most people call it the line of best fit. And, you know, it's like that green line that I tried to draw there. It's also called the linear regression model. And the technical name for it is the least squares line. I'll write those words up on the board at some point. We want to be able to, and I think I'll do a lettered list here, find and interpret the y-intercept We want to be able to find and interpret the x-intercept we want to be able to, and actually let me pause right there. I think we were talking about this last time, or maybe the time before. No, I think it was last time. I think it was Wednesday. These instructions, find and interpret. Remember, that's a two-step process. There's the find part, and then there's the interpret part. And so that's, we need to remember that when we go into this analysis. We want to be able to interpret the slope number we want to be able to classify what's called the correlation coefficient. And we want to be able to interpret, yes, what's called the coefficient of determination. Determination. And I'll explain what all these things mean as we get in, when we get into it. And then typically what we want to be able to do is to use the line of best fit or the equation for the line of best fit to make a statement or a prediction. Use the equation to make a statement or prediction. Because again, the whole spirit of this analysis is the idea of being able to predict one thing based on another thing. And in this powerboats versus manatees example, we want to be able to predict the number of manatees killed based on how many registered powerboats there are. Okay, so let's pull out this equation here and start going through this list. And what you'll see is that some of these, there's 6 things there in this list. Some of them are really simple and straightforward. Others take a little bit more thought. Okay, so our example that we're working through right now is the powerboats versus manatees. And again, I cannot emphasize enough how important it is to be clear about what the two variables represent. So our explanatory variable is x, and that is the number of registered powerboats in thousands. And our response variable, y, is the number of manatees killed. And our line of best fit we came up with y is equal to -32 plus 0.12 times x. And let me put these other vocabulary words up here. This line is also called the linear regression model. Regression model, or the least squares line. So let me go ahead and underline those. Model or the least squares line. And what I call this equation depends on who I'm talking to. If I'm talking to a stats class, I'll typically call it the line of best fit. Sometimes I call it the linear regression model. If I'm talking to a bunch of mathematicians, I'll probably call it the least squares line. So all three of those things are synonymous. All right, so let's go through this list here. So we'll start with the y-intercept. So the y-intercept. Now the y-intercept is going to be described by an ordered pair. That's the nature of the data and how this line works. We're talking bivariate data. And so it's going to be an ordered pair. So we're going to have a value of x and we're going to have a value of y. And to find the y-intercept, that happens when x is equal to 0. Right? So keep in mind that our ordered pairs are going to look like a value of x, comma, a value of y. So the y-intercept happens when x is equal to 0. So you set x equal to 0. So what you do is you come back to this line of best fit and you put in a 0 for x. And if you put in a 0 for x, 0.12 times 0 is 0. And you're sitting there with that y equals -32. You get y is equal to -32. So there's the y-intercept. It's that ordered pair. And that, folks, is the find part. Now, the interpret means put into words what those two numbers mean. 0 what? 0 registered powerboats, right? Because x is registered powerboats. So 0 registered powerboats, -32 manatees killed. So if there are no registered powerboats, -32 manatees will be killed. That's what that ordered pair represents. So that's the interpretation of that ordered pair. Now, that is nonsense. That makes no sense whatsoever. So I'm just going to jot that down. And what you'll see is that there will be plenty of situations where the y-intercept or the x-intercept, or possibly both, won't make any sense whatsoever. sky? Well, we want to be able to recognize that. So one of the things that's difficult for students to do is to decide that, hey, that's nonsense, and then just move on. I've seen students dwell on this, and they say, oh, I gotta get some meaning out of this. What does this mean? 0 registered powerboats, negative 32 manatees killed. How can you have a negative number of manatees killed? Negative manatees killed? Well, that means manatee births. That means manatees showing up. Ah, yes, in the absence of powerboats, manatees would flourish, and there would be 32 births every year, you know, and it's like, she's like, that's bullshit, you know? This statement is meaningless, it's nonsense, just move on. Okay, so we've got that. Let's go find the x-intercept. So hopefully you have this list written down. I have it in my head, so I'm going to erase it because I need this panel here. Let's see. I'll erase the part that we've already done. Okay, so let's go to B in this list, which is going to be the x-intercept. And the x-intercept is going to be an ordered pair. There's going to be a value of x and there's going to be a value of y. And to find the x-intercept, you set y equal to 0. So here's where I'm going to do a little bit of simple algebra. I'm going to come back to this equation. I'm going to replace that y with a 0. So I end up with 0 is equal to negative 32 plus 0.12x. And then I'm going to use some basic algebra to solve for x. I'm going to erase this. Okay. So what I want to do is I want to isolate that guy right there. So what I'm going to do is I'm going to add 32 to both sides. Let's start there. 0 plus 32 will give me a 32. Those are 0 out. I'll have 0.12x. Now that's 0.12 times x. So I'm going to divide both sides by 0.12. And then I'm going to run this through a calculator. Clear that out. So 32 divided by 0.12, I get x is equal to 266 point lot of sixes. And again, I'm going to go ahead and round this off. I'm just going to call this 267. So there's the x-intercept, and that's the find part of this. The next thing to do is to interpret this. So 267 what? 267,000 registered powerboats, 0 manatees killed. So here's the interpretation. If there are 267,000 registered powerboats in the state of Florida, no manatees will be killed. Will be killed. that's all right. And then you have to stop and think, okay, well, does that make any sense whatsoever? Or does this statement also get a nonsense attached to it? And I'm going to argue that this actually does have meaning. Because, and here's my thinking. Let's suppose in the state of Florida, in the entire state of Florida, there were only 1,000 registered powerboats. I'm going to argue that that would pose little or no danger to the manatees. Because that 1,000 registered powerboats in the entire state would not translate into enough boats in the water at any one time to really endanger the manatees. If you increase the number of registered powerboats, then you start to run the risk of manatees killed. And so what this says is that once you have more than 267,000 registered powerboats, now we're going to start seeing manatees show up dead. But up until this point, there will be virtually no danger to the manatees. And so this model is predicting no manatees will be killed. Cross over this point, and now we're going to start to see manatees killed. So I think this interpretation actually holds water, no pun intended. I think it's actually okay. So I'm going to leave it. I'm not going to say, it's nonsense. All right, so these two are fairly straightforward. If you're bewildered by the algebra that I have done here, come and check in with me during office hours, or check in with the tutors at the MLC or the ILC and say, hey, Jay did this and I don't understand it. Can you explain basic algebra to me? And they'll be happy to do so. I will be happy to do so in office hours as well. Okay, so what's next in the list? We've got the two intercepts. Now let's go to the slope number. This can sometimes get a little bit tricky. So I think this is C in our list, which is interpret the slope number. Now the slope number is this guy right here. In the form that we're using, it's the value of b. We're using that a plus bx. And the number out in front of the x, what's called the coefficient out in front of the x, is the slope number. So what we've got is we've got b is equal to 0.12. And again, here is a connection with some elementary algebra. And it's, okay, well, what is a slope number? By definition, if you go to algebra, let me erase this. Let me just sneak a little note in here. So from algebra, the slope is a fraction. It is change, I need more space. Actually, let me use an abbreviation here. I'm going to use the uppercase Greek letter delta. So the uppercase Greek letter delta in science is used to indicate change in. So let's just jot that down. That means change in. So by definition, the slope number is the change in the y value divided by the change in the x value. So what I'm going to do is I'm going to take this decimal here, and I'm going to give it a denominator of 1. And what that allows me to do is to see this number, this slope number, as a fraction. And so that's going to be, this is going to be the change in y, and that 1 is going to be seen as the change in x. So let me come over here. I'm going to leave this part up here. Yeah, okay. So again, it's critical that you keep in mind what x represents and what y represents. So the change in y, that's going to represent the change in the manatees killed, and this is going to represent the change in the powerboats. But we have to keep units in mind. One what? What are the units for x? The units for x are thousands of registered powerboats. So that's 1,000 registered powerboats, and that is 0.12 manatees killed. Let me just delineate this a little bit. So what this fraction says right here is for each additional 1,000 registered powerboats, an additional 0.12 manatees will be killed. Which to me sounds like a weird thing to say. Because how do you kill 0.12 of a manatee? And to make sense out of this, I would like this to be a whole number. And so let me show you one of the tricks that you can use to turn this into a whole number. So check this out. If I take 0.12 over 1, if I multiply this numerator of this fraction by 10, it'll move the decimal point one place to the right, and this will become 1.2. But if I take this and I multiply it by 100, it'll move that decimal point 2 places to the right. So what I'm going to do, I'm going to try this and see if it'll work. I think it will. Is that I'm going to take this fraction and I'm going to multiply top and bottom by 100. That will turn this into 12 over 100. And now let's put that into words. Let's interpret what that says. So what this says is for each additional 100,000 registered powerboats, an additional 12 manatees will be killed. And I don't like what it says, but it reads, right? I mean, I don't like the idea of 12 manatees being killed. That sucks. But as a mathematical or scientific statement, that reads a whole lot better than this one does up here. So I like that. I think I'll stick with that. Now, there's another type of trick that you can use to make the slope number look good. And I'll show you that next time. Okay, so we got halfway through that lettered list that I put up there. We got the intercepts covered. We got y-intercept, x-intercept, and slope number covered. We still have the remaining 3 to do, and I will do that on Wednesday. So I'm not going to bother to assign any homework problems from chapter 4 yet. I want to get through our discussion of linear regression analysis completely, and then I'll turn you loose on some problems in the textbook. What I want you guys to do over the next 48 hours or 46 hours is to rewatch this lecture as necessary. Get the data into your calculator and try to reproduce all the work that I did today. Watch the video, the YouTube video on our Canvas page. That shows how to do simple linear regression analysis on the calculator. I think that will be helpful. It's like a 5 or 6 minute video. It's not very long. And on Wednesday, we'll pick up this example. We'll finish off that lettered list that I put up there. And then we will open up a second example of this. And I think we'll be okay. You might be feeling a little overwhelmed right now going, well, you haven't seen the whole picture yet. So once we go through this finish this example on Wednesday, go through a second example on Wednesday, I think you'll be just fine for this linear regression analysis stuff. Okay, so let me come back over here. Just about out of time. Hello, sit down and bring this camera back. Oh, okay. So I'm gonna call that good for today. And if you have any questions, I'll hang out for about 5 more minutes. And otherwise, I'll be in office hours later today at 2 o'clock. And I'll be in office hours tomorrow at 11 o'clock. And if I don't see you at either of those places, then I will see you, hopefully, Wednesday morning at 8. Okay?
Thank you.
Thank you.
Very welcome.
Jay, I have a question about the first quiz. So I have it here and I marked it up when you were going over it in red, and I wanted to see if there's any way that like I can get credit for it, just because when I submitted the quiz, it does, like on my phone it says successfully submitted.
Yeah.
But when I try to find the file, it's not there.
Well, bear with me. Actually, let me go ahead and stop this recording.
Okay.